Cool! Hi! Welcome to another video. So last time I've done the video about blockchain development roadmap, and that seemed to help few folks that I've heard back from. So I figured I'm gonna do one more, a little bit theory heavy talk, but I'm gonna sneak in some code as well this time. So the topic for today that I wanted to talk about is private keys, how they work in blockchain. I put here Ethereum. I don't know how I'm gonna name the video yet, but I put Ethereum, but it's the same thing applies to any blockchain that is Ethereum compatible, like or your Avalanches and Binance Smart Chains and Polygon as well. So let's dive right in. So a section in here, you can see intro, private keys, public key, signature. Then we're gonna talk what the mnemonics are, and then finally coding time. So what I would like to build here is just a simple private key generator. It's gonna be fun. So let's stick to it. Cool. So why would you wanna care about private keys? So when I was starting up in this blockchain journey, private keys always seem kind of daunting, or it's kind of weird, difficult thing to understand how it really works. It's just that private keys, keep it private, but then it's actually very good, I think, to understand how it works. Because when you ask for advice, what you do with private keys, you get standard answer: buy a hardware wallet and use that, which is true. It's a very good tool. But I think even better, arguably, is to just learn about how the private keys and public keys works, what the relationship is, and what to avoid. So that can step up your security, confidence a little bit. So private keys, they are part of a pair. There's a private and public pair. These kind of things are called asymmetric cryptography. It's like a math/programming term being used. And it's not the only example we have here in blockchain. We use this every day on the internet. So if we look here, for example, and then I don't know, if we go to Ethereum, doesn't matter. Whoa. Here you can see this little lock icon, and that's because this is using HTTPS, and the S here stands for SSL, or secure, I guess. But it's using again asynchronous cryptographic tool, which is in this case the SSL certificates. But even there, we have a private and public key. In that protocol, it's called certificates, private key, so on. But the basic thing is the same. You have a private and public part. What we use in HTTPS, we use it for encryption. So we take whatever message I'm sending to, what was that, Google or somewhere, and whatever we get back, and then the server used their private key to kind of decrypt and read what I sent in. So that's what we use that's what we are all familiar with, because we use that on an everyday basis. And same goes for FTP as file transfer protocol, secured. It's also with SSL. It's all these protocols that use the same mechanism for that. But in crypto or in blockchain, what we use that for is a signature. So we don't care about hiding the content so that people can't read it in the middle, which is what the HTTPS is for. But we want to verify both the sender of the transaction and then also the data in it. So that's why we use those private and public keys here. And then I have this point, which I forget what I want to talk about, but I think I wanted to like just show it in real life. So this is just a test wallet that I created for this demo. I'm gonna do this. And here, if you copy this to clipboard, I'm gonna paste it here, you get this, which is your address, right? And then if you would go somewhere here, you can do export private key. And just to do password again. And you get a private key. So this is how your private key looks like, right? Again, I'm not using this account for anything, so that's why I'm comfortable sharing it. Cool. So let's talk more about private keys. So private key in here in blockchain is actually just a random number. So it's a really big one. So it's a 64 random hexadecimal cipher decimals, I guess. So what hexadecimal numbers are is just that, you know, you have a 10-based language, so you have a 0 to 9. Then you have a maybe binary-based language. Then you would have just, you know, 0 to 1. Let's do this. But then you have a hexadecimal, which is 16-based language, and then you have, you know, 0 to 15. But because we want this to be like a 1 character and 15 is 2, what we start using there is letters. So you go 0, 1, 2, 3, 4, 9, and then A, B, C, D, E, F. So we go 0 to F. You know, so there are different reasons why we would use 16-based math other than 10. One of the reasons here is that it's just more concise. So if this is a 16-based number, this is example of a private key, then it takes just much smaller space. So it's for a human, it's easier to copy and stuff like that. You can imagine it would take less memory if it would be stored as a string as opposed to 10-based number. But numbers are of course stored, you know, in binary system in the end anyway. So this is a perfectly valid private key, number 1, right? I can just take this, and I can, how do I do that again? I can import account, put in the number 1 here that I copied, right? Just copy the number 1 here, and I have an account here, and then I can look on the Etherscan, and you can actually see that there are people doing operations like 48 minutes ago on this account, because this is if you have this private key 1, which now you all have, you can like move money out of this wallet. So if somebody by mistake sends some ether in, like this poor person, you can take it out. Like this is probably too small amount to bother, but you can do that. And what you can also do is just play the private key lottery, right? You can try different numbers. So you could try, you know, number 2, or you could try number 2, you can try number 42 or something, and they are all valid. So, you know, I'm not gonna lie, when I was preparing for this, I did try a bunch of numbers. They all were like basically empty wallets, but you can try yourself. It's kind of fun. Also, one note, it's that there's like really a lot of combinations you can do here. I think I saw somewhere on Reddit, I guess, there was some good illustration how many numbers you can do, and it was written there that it's like if you count all the sand on the earth, and then for each piece of the sand you would have another earth, and then you sum up all the sand in it, then that's many private keys you get to generate. So it's like really a lot of them. You can throw them out a lot. You can programmatically create them and you know, use that. So you could imagine some sort of software or some sort of project where instead of airdropping some existing address, you would create a new address, put the asset in that address, and then share the private key with a person, right? It's also a thing you can do. Cool. So that was private key. That's the most crucial part. And obviously it's private. It's meant to be private. You're not supposed to share this because whoever has this has a full control over the account. Like I can, transfer money from that number one account. Nice. So what's public key? Public key is just derived from private key. What we're using here in blockchain is ECDSA algorithm. So when we talk about this encryption comparison to SSL, they're using maybe RAS algorithm or something like that, where we would... Oh no, that's probably nonsense. That's something else. Never mind. So we're using this algorithm, but it's a different algorithm than what you would use in HTTPS. And the reason why it's different is that what we're trying to achieve is very different. In encryption in HTTPS, what we need is the result needs to contain the whole content that you're trying to pass through this very unsecure internet thingy. While here, we don't care about that. We don't want the result to contain the source. We just want the source to be like verifiable with that signature. So in my head, that sounds like a simpler problem, which is why we can have a different algorithm. I mean, there's always drawbacks to every solution, so it's the trade-offs, right? So if you have a simple problem, you get to make something better. You might, so this algorithm might be like stronger in some cases. I don't know. Anyways, this is algorithm. We get to derive, meaning create, or like, as you saw me do with the MetaMask just a minute ago. I put in a private key and then MetaMask print out they figure out the public key and then address as well. And that's the last point here, that the last 40 characters of an address of the public key pardon, is the address of the account. So the address you see here, or you don't, but that full address, or here, that's not the whole public key, but it's the last 40 characters of the public key, or like excluding the 0x, because 0x in programming languages means this is hexadecimal constant behind it. So this is just like letting you know this is hexadecimal. Which is, we saw what the hexadecimal is. It has the letters in it, so that's why there are letters. But this is still a number in the end. Cool. Cool. So let's talk signature. So when you do any transaction, we attach a signature to it. This is not encryption, as I mentioned before. We're not trying to encapsulate everything in that signature, but we're just trying to have a way to verify the content. And there's also like a random number included in building this. It's not that important, I guess. To avoid... because then you could kind of guess the private number. Because you could then guess the private number if you would have the same content and two signatures and they would be, always the same, or they wouldn't be the same. You would have two contents, they would be different contents, and you would have a different signature. You could, in theory, make it easier to like figure out the private key, which you shouldn't do, right? But from the signature, you can always get a public key from it. So you can kind of figure out, again, using this fancy algorithm here, what the public key is, like the pair to that private key. And then from the public key, as we said, the last 40 characters, those are the address. So that's how you verify the signature. You take the signature, you derive a public key, you look at the last 40 characters and compare to the sender from. And if that matches, you're all good. And you can do a similar thing with the content as well. Cool, hope that makes sense. I feel like I'm running quite quickly. Hopefully it's fine. Okay, so let's look at one more thing before we do code. Do code, nice. Mnemonics, what they are is just a way to, because as we mentioned, you can have many private keys, and it's probably a good idea to use different private keys for different purposes. So, you know, diversify. I remember we had this professor in uni, and he was asking the whole class, like, what's the best investment you can do, right? And there were people saying, oh, you should buy a flat, like real estate. There were some just do funds, just stable, you know, funds in stock market. And then he said, and then everyone expected him to say something, right? Some vehicle that is, according to him, the best. And he said, you should know that the diversification is your best friend. So you do a little bit there, a little bit there. And same applies here, I think. Like, you want to have different private keys and different accounts for different purposes. Or maybe same purpose, but just like so that you have it split. And Mnemonics is a way for you to do that with a single thing to remember or write down on a piece of paper. Because Mnemonics is a more human-friendly way to kind of store multiple private keys. How that's done? So let's have a look at an example. So again, if we look at this, I think somewhere here, allowance maybe, security maybe. Right, you get this is the mnemonic, like a bunch of words in English that you can use, and then there's an algorithm that helps you generate several private keys from that. So let's put an example here. And why would you use that is, as I mentioned, that you can store just one thing. Oh, damn it. Sorry, I opened something by mistake. Okay, just gonna close it. So as you can see, this was the mnemonic I used. And now if we look at account 1, which was generated from this mnemonic, the address ends with 768. Let's just paste it here. And if we would, you know, lose access to this computer, or I'm just gonna remove the extension, right? For some reason. And then I'm gonna go and install it again. What I'm trying to demonstrate is that we would get access to all these accounts again. And not just the first one, but any of those accounts. So we don't need that. And if we open MetaMask here, it's gonna greet us, and then we can, I already have a secret thing. Agree, of course. And then we can go here, take this mnemonic thingy, paste it in here. And then we choose a new password. I'm going to talk about the password in a second. Hold on. And then you can see that this first account, I just copied it, is actually the same one as we had before. And that's because there's just one way to derive the private key, so the order will be always the same, and you get all these keys. Cool. And the last thing I wanted to mention is the password in MetaMask. So what's that, right? We talked about private keys, we talked about mnemonics and public keys, addresses, but we never mentioned password. But whenever you open a MetaMask, it asks you for a password. So what's that? So this kind of wraps back to the beginning of the conversation. You put in a private key into this plugin, but what does the plugin do with it? It needs this private key to sign transactions, so it needs access to it. It needs to remember it somehow, and it needs to work even if you turn off your computer and all. and you really don't want that to be sent to like Infura or whatever, you know, server that MetaMask is using, the private key. So the solution is that the plugin here will create a local file on your computer, encrypt it, and then using this password you get to it will encrypt it and then decrypt it again, right? So only if you have this password you have access to this private key and you get to read this. But that has nothing to do with the generation of the private key. So if you move the seed phrase to some other computer and you don't have this password, it doesn't matter, because the seed phrase generates the private key. You don't need the password in order to generate the private key. The private key is only access to this local file that is on your computer that stores the private key, if that makes sense. So then again, when I reinstall with different seed phrase, I could have chosen a different password and used that instead. And then also that means that if somebody like steals your hardware, like your laptop and the hard drive in it, they don't have access to the private key either, because they don't have a private key. And it also means the attack vector for you to lose the private key is kind of difficult, because unless you type the private key, actually, they would have to steal both the file and the password to unlock it. And because those are handled by two different systems, you would have to have, pretty sophisticated attack, which is possible, but just unlikely, I guess. Cool. So that's that. Yeah. And now let's try to code something. I'm gonna create a new file. How do I do this? New file. Let's call it private keys JSON. Okay. I'm also gonna open a terminal down here, and I'm gonna make private keys JSON executable so that we can run it like this. Nice. So let's just try this works. And then result. Right. And we can have a variable. Let's call it the result. Very original. Right. And then if we go down here, right, private key, we get some error. Oh, it probably doesn't know this is, yeah. Yeah, this is good. So we probably, let's close this. Probably need a shebang thingy, like this. So this line tells, my bash script here that it needs Node to run this. So now it works. Because otherwise it was just a bunch of letters and it thought it's maybe a shell script or something. So now this works. If we go back to the nodes, we said that the private key is composed of 64 random hexadecimal characters. So let's do that. So let's do const length equals 64. And then we're gonna just do for loop. Let's go with counter, as long as it's less than 64. And we can just do result plus equals whatever, A for now. So now we should get private key, which is just a bunch of A's. This is already a valid key, but it's not very random, right? So let's figure that out. So to get a random number, you would just do like a math random. Do the random? I thought you do round. Let's see. And let's just put it here. And let's well, you know what? Let's just print it here so we can see what we're dealing with. And again, if we run this, we get these numbers. So math.random generates a random number based on like your time in your computer, based on some networking, I hope. So it's semi-random, right? Because there's no randomness in computers, but it just uses a lot of things that change a lot from computer to computer and change often. And then based on that, it has some algorithm that generates a random number. And this random just returns number between 0 and 1. But as you can see, there's some precision going on, so it's going to, negative numbers. Not the partial numbers, I guess. So the easiest way I can think of to generate a private key is just go character by character and do 0 to 15. So that means that we want 0 to 15, not 0 to 1. To achieve that, you can just multiply this by whatever you want, like 15 in this case. So if we do this now, we get like numbers like 5, 14. So that's good. But we don't want that partial part, so we can just math round. Is it round? I think it's round. No? Isn't it round? Yes. I don't know why I'm so confused. So if we do math round, it's gonna be just the integer part of it. Nice. But now, as you can see, the character is just still printed as 2 characters, right? That is higher than 10. We want this to be actually A instead of that. Turns out there is a way to do this. It's toString, and then you pass the type of math that you want to use. So in our case, 16. Now if we run this, you're gonna get D, E, all the letters. So then instead of A, we can put it this thing. And if we run this, ta-da! We're basically done. So this is it. This generates a random wallet or random private key that you get to use. So you can take this and save it somewhere, but you can also like import it to MetaMask here. And then you have an account that nobody ever used before, because the chances of that happening are just like non-existent. So I guess that I hope that helped. So this private key generator is very simple, but it's very nice because you can trust that we're not sending the private key to some server here. Obviously you've written it, so you have to trust yourself that this still works. But that's the way I'm generating private keys anyway. Because I don't want them generate on some website, because then I don't know, or a plugin even, because I don't know if these things get sent somewhere else. Also, one thing I haven't mentioned is what's the benefit of using Mnemonics, and what's the drawback of using them. So Mnemonic is very powerful. You get one thing to access all of these passwords, all of these private keys. But it also means that you have one thing to access them all, right? And then if you're a developer, you sometimes need to inject your private key somewhere. You could inject Mnemonic that somewhere, like the server, to do something, but then you giving that server access to all these private keys that they can generate. So in that case, you would probably use a private key instead, not Mnemonic, because you just want to share one account with that server, not all of them. Yeah, so I guess that's that. Cool. I realized this was a little bit, I don't know, sketchy video. Not sketchy, but like confusing. I went through a lot and quickly, so please let me know if that wasn't clear or helpful at all, or just confusing, and I'll try to adjust for the next time. But yeah, thank you so much. Hope this helped somebody. Bye.